Good morning, physical science students. Today we are officially starting Unit 3. It is our first lesson on waves. We are looking at specifically Standard 9A, introducing some of the relationships between our different types of waves. So starting with what is a wave? A wave is a rhythmic disturbance that carries energy through matter or space. So a wave is something that carries energy. It could carry energy through matter or through space. Now, typically instead of saying matter, we're going to say medium. So medium is just different types of matter that we could actually see. The wave is going to transfer the energy through the material. Of course, our different phases of gases are going to be our different mediums, solids, liquids, gases. You could have combinations. And certain waves are actually able to travel without a medium. There's only one type, but it is able to actually travel through space. And I just answered that own question. So do all waves require mediums? No. We will see shortly where mechanical waves do require a medium, but electromagnetic waves do not. Now, if we remember in our previous unit, electromagnetic was just a fancy word for light. So light waves do not require a medium. They are the only ones that can travel through empty space. So this is a nice visual representation of a wave. If you've ever been to a sporting event, you may have actually done it. It is energy moving through a medium. So the medium in this particular case is the people standing and sitting down. So waves tend to repeat and have predictable patterns. Now, waves carry energy from one place to another. Waves are caused by some type of a vibration, and we can actually use waves to do work. Some waves are actually used to move objects. So the waves carry the energy, and the vibrations transfer the energy from one position of the object or medium to another position. As the waves carry the energy, the particles move in the medium. And the direction of the motion determine the type of waves. So notice the one that we saw a moment ago, the particles were moving up and down, while the wave was moving left to right. Well, that indicates a particular type of wave. Now, there are two main categories for waves. One is mechanical waves. Mechanical waves is a wave that must travel through a medium. It cannot travel in a vacuum. An example of mechanical waves, of course, is like an ocean wave, or the wave that we saw with the people, or even a sound wave. Those are all mechanical because they cannot travel through empty space. On the other hand, the other type of waves are our electromagnetic waves. These are our light waves and rays that are able to travel through empty space. They do not require a medium. So they are the only kind that can be transferred through a vacuum. Examples, of course, include visible light, gamma rays, microwaves, UV rays. There's a whole spectrum of the electromagnetic waves that we will see later in the unit. So the motion of the medium determines the type of wave. As I said a moment ago, there are two major types of waves, and how the wave and the medium moves determines what it is. So earlier we saw the people who were standing up and down and then sitting, but the wave was moving left to right. That is a perfect example of a transverse wave. The wave moves perpendicular to the motion of the particles. Unlike a longitudinal wave, where the wave and the particles move parallel to each other. So the L's at the beginning and end kind of help me remember that longitudinal waves move parallel. The T at the beginning helps me remember that transverse waves, the energy moves perpendicular. Two illustrations of each of the types of waves. Notice the transverse wave. That's probably what you're used to thinking of when you think of a wave, because that's what we see in when we're seeing the ocean, or when you see people in a stadium, or even like a wave with a jump rope or spring. The particles are moving up and down. The wave is transferring to the left or the right. Versus the longitudinals, that's our sound wave. It requires a forward and backward motion with the particles, and the wave moves left to right. So they're moving parallel. So our transverse wave, the medium vibrates perpendicular to the motion of the wave. So my particles are moving one direction and the wave moves perpendicular to it. It gives us that nice, pretty uppercase T. Examples include water waves and electromagnetic waves. Our graph here is showing a nice, pretty longitudinal wave, not longitudinal wave, sorry, transverse wave, and we could actually use this to determine the wavelength, the amplitude, rest position, all types of things that we're actually able to identify in a transverse wave. So if we're looking at the parts of a transverse wave, the highest portion of the wave is called the crest. And all of the highest portions are all called crest. So even though I only had one labeled in the image, they're still all crest. The lowest portion of the wave is the trough. So I think, pigs eat from a trough. It's the bottom of a curve. The crest is the top of the curve. Amplitude is how far the wave moves from its rest position. So the rest position is kind of just the midpoint between the crest and the trough. And the amplitude is always measured from that rest position. Now we can measure it from the rest to the crest, or we can measure it from the rest to the trough. Either way, it gives us an idea of how much energy is in that wave. A larger amplitude means more energy. And I think I just said that. So the larger the amplitude, the more energy that is carried by the wave. If you've ever seen in movies a tsunami wave, those waves are carrying massive amounts of energy, which is why they're so large compared to your normal ocean waves. The last thing on our transverse wave is the wavelength. The wavelength is the length of one wave. You can measure it from crest to crest, trough to trough. Those are probably the two easiest positions to measure from your wavelength. But a wavelength has to include both the up and the down portion of the wave. So if I'm doing it from this midpoint, I've got to include the down and the up. So the blue line represents one wavelength. Any three of the blue lines, any one of them, represents the length of one wave. Pick what makes the most sense for you in terms of how to identify wavelengths and use that to see how long a wave is. Like I said, crest to crest or trough to trough are typically the easiest to measure, but yes, you can do it from its rest position. Now, the time it takes for one full wave to pass a certain point is called a period. So a period is a measurement of time. It's the time it takes for one full wavelength. And for some reason, period, its variable is that upside down y. It's called a lambda. So you will need to make certain that you know the different parts of a wave. Additionally to the crest and the trough, anytime the wave crosses that resting position, you have what is called a node. A node is just where that wave is crossing the rest position. Again, we have our wavelengths, and we also have our amplitude. And amplitude can be measured from rest to crest or rest to trough. If I was a student taking notes, I would make certain to sketch this particular illustration into my notes so that I have all of the key anatomy for a transverse wave on one simple page. So remember that your amplitude corresponds to the amount of energy. The taller the wave, the more energy that wave has. So longitudinal waves. Longitudinal waves are also called compressional waves, and that's because our particles are moving back and forth. They are compressing together in order to transfer that energy. The medium moves in the same direction as the motion of the wave. So if my medium is vibrating left to right, then my wave is going to move left to right. Examples of these are sound waves. We can also see these with slinkies and springs if we take and move them back and forth. So not up and down. We are vibrating the slinky back and forth. When you see longitudinal waves, you have parts where the waves is very, very spread out. Trying to illustrate that with the blue arrow. And then you also have parts of the wave where the particles are highly compressed. Each of those different portions of the wave has its own terminology. Now, it's interesting to note with this graphic, if you pay attention to the red dots, that even though we can see the wave moving through the medium, the individual particles don't actually move that far. So they're just moving left to right in a very small position, and the wave itself travels through the entire medium. So nice visual here at the top of just a single wave traveling through. I just realized that I was doing that over and over again. So the area of the wave that is the particles highly, highly close together is called the compression. They are compressed together. The area where the particles are more spread out, that is called the rarefaction. So compression, the particles are close together. Rarefaction, the particles are spread out. So a different visual, but we notice that the particles are more spread out. That is the rarefaction. I can't say it this morning. That's the area where the particles are not close together. Compression is where the particles are close together. And again, our wavelength is the length of one wave. So in a longitudinal wave, we have to make certain that we include both the compression and the rarefaction. So I can measure my wavelength from one compression all the way through the end of the rarefaction, or I can do from the rarefaction to the end of the compression. Either way, that would be one wavelength. So in this particular illustration, I can see, so one wavelength, two wavelengths, three, and not quite a half, because the rarefaction was, 5 rings, and that's not quite 5. So roughly 3.5. Now, in a longitudinal wave, the number of compressions is going to correspond to your energy. The more compression zones that you have in a single longitudinal wave, the more energy it has. So when we are having more compressions in a smaller space, we're going to have a higher amplitude. So great summary of both terminologies for both our longitudinal and our transverse wave. This unit, if you have not already noticed, is very, very terminology heavy. So make certain you're able to identify the position on an illustration of each of these things, as well as knowing just a general definition of what they are. So one last thing for today, we're looking at how we measure waves. We already mentioned how a period is the amount of time it takes for a wavelength to travel a particular position. Well, frequency is the number of waves that pass a point in 1 second. So frequency has its own unit of measurement. It is called hertz, or you can think of it as 1/seconds, because 1 hertz equals 1/seconds. If you get to a high enough frequency wavelength, it hurts your ears. So that's an easy way to remember the unit for frequency. So assuming that my illustration is 1 second, notice how the top image only has 1, 2.25 wavelengths in 1 second. So its frequency would be 2.25 hertz. Versus the bottom one, we can see that we've got more crest. So it's easier to determine that it's going to have a higher frequency, but include all of the crest and all of the troughs. We can see that we have 3.25. So 3.25 hertz would be the frequency of that second wavelength. It's at a higher frequency because more waves pass a given point in 1 second. Now, shorter wavelengths end up having a higher frequency. So notice my wavelength is smaller, therefore my frequency is higher. That is an inverse relationship. Inverse relationships mean when one of them goes up, the other one goes down. So longer wavelengths, like we have on the top, means lower energy, lower frequency for our longer wavelengths. Shorter wavelengths are higher frequency. Now, it's interesting to note that when we're talking specifically about sound, that lower frequency sounds are harder for us to hear. Not only are they harder for us to hear, but they tend to sound like low bass notes. Our higher pitched sounds tend to have that higher note, that higher sound. So picture, a baby squealing. That would be a sound that would have a higher frequency. So we can actually put frequency together to kind of get our wave speed. So we know that frequency is the number of waves over time, and we know that our period is the amount of time that it takes for one complete cycle. So we put this together, we're determining a lot of information about our waves. Again, frequency is measured in hertz. Period is, is measured in time. So we can easily go from one to the other. If I put 1 over my period, I will get the number of waves per time. Or if I do the number of waves per time, I would get 1 over period. So velocity, remember, velocity gives us an idea of how quickly something is moving. In relationship to waves, it is the speed of the wave as it moves forward. So remember that upside down y, that lambda is our variable for wavelength. Wavelength is measured in meters. Frequency is measured in hertz, or 1 over seconds. And if we take meters times hertz, we get meters per second. So since we're talking about moving forward, this is a velocity, and it's measuring how quickly a wave moves. Now, wave motion, specifically sound, the speed of that wave is dependent upon the medium. So if we're looking at sound waves specifically, sound is going to travel fastest in a solid because those particles are right next to each other. As soon as one particle moves, it's going to bump into the next one. So sound is able to move very, very quickly through our solids. Our liquids, it moves a little bit slower because the molecules are spread out just a little bit more. So it takes a little bit more time for the particle to transfer that energy from one position to another. Gases are actually where our sound moves the slowest because the atoms are really, really far apart. So it takes a considerable amount of time for one particle to hit another. Now, if you've ever happened to be near a train and you can hear it coming, put your ear down to the ground you'll hear the train through the ground faster than you'll hear the train through the air. That's because that sound wave is moving quicker through the solid and slower through the gas. So solids, remember, our particles are very, very tightly packed. They have no choice that when one of them moves, it transfers that energy very quickly to the next particle. The liquids, our particles are spread out just a little bit more. They're able to kind of slide past each other, so it takes a little bit more time for those particles to transfer the energy. So not as fast as a solid, but nowhere nearly as slow as a gas. My energy would transfer through liquids. And last but not least, we've got our gas. Our particles are really, really far apart. It takes considerably more time for that particle to transfer the energy. Therefore, specifically like sound, it's going to travel much slower in a gas. I love this particular graphic here because it's a good visual representation of how sound travels through each of the mediums and kind of gives you a good representation of how much faster our solids and liquids are compared to that gas. So notice my gas, my particles are much, much further apart. Therefore, it takes more time, almost double the time, for that energy to transfer through that gas as it does through the solid. So in terms of our frequency, I mentioned this earlier, that frequency is related to our period, and that if I were to take 1 over my period, I would get my frequency. So notice the amount of time it takes for a wave to travel a certain point would be my period, and my frequency is the number of waves per second. So there is a relationship between those two. This top kangaroo has a shorter wavelength, therefore he's got more energy. He is able to, lost the train of thought. Bottom kangaroo has a longer wavelength. He has less energy that he is transferring through the air. And that is it for today. Make certain that you complete the activity that is posted in Google Classroom.